Next, we will take a look at how temperature affects spontaneity of the process. We are going to use the delta T equation to help us understand the effect of temperature better, which is delta T equal to delta H minus T delta S, which is the same as delta H add to the negative T delta S is mean the same thing here. I'm going to use this equation to help us understand how temperature affects spontaneity. When the reaction is endothermic, delta H would be a positive value. And if you add this term to the negative T delta S, and because delta S is positive, if it's positive, then the positive multiplied by negative is going to give you a negative value for this term. When the sign of the heat produced from the system is the opposite of the sign of the heat that transfer to the surrounding, then the sign of delta G will be depend on temperature. If the temperature is at low temperature, this negative term will be small. The small negative add to a bigger positive. The result of delta G would be positive. Therefore, in this case, for the endothermic, the reaction would be non-spontaneous at low temperature. However, if you have the reaction at high temperature, which means that the high value of the temperature multiplied by the entropy change, this side right here would be a big value of the negative. The big value of the negative will override the positive from the enthalpy. Therefore, the overall delta G would be negative. It indicates that for the endothermic reaction that depend on the temperature, the reaction would be spontaneous in the forward direction at high temperature. Next, let's take a look at the scenario where the reaction is exothermic, which is the delta H is negative. The negative delta H will add to the negative T delta S term. If in this case the entropy change of the reaction is positive, you will see that the positive multiplied by negative, you are going to get this term as a negative value. In this case, you have negative value from delta H and negative value from this term right here add together. Therefore, the overall delta G will always be a negative value. Indicate that this reaction will always be spontaneous in the forward direction at any temperatures. Therefore, in this case, temperature doesn't have any effect on spontaneity. Next, let's take a look at the scenario when you have the reaction which is endothermic. So the delta H would be positive in this case. When you add this positive delta H with the term of negative T delta S, if you have the reaction where the entropy change of the system is negative or the dispersal decreased, this negative term multiplied by negative is going to give you the overall of this term to be a positive value. And if you have the positive enthalpy change, add to the positive of this entropy change term, you will see that no matter what these two add together, it will always give you delta G to be a positive value. Positive delta G tell you that the reaction would be non-spontaneous in the forward direction at any temperature, and it tell you also that in this case, temperature doesn't have any effect on spontaneity because the reaction will always be non-spontaneous in the forward direction. The last scenario is when you have exothermic reaction, so the delta H would be negative. When this negative add to the negative T entropy term, you will see that if the entropy is a negative value, the negative value multiplied by the negative, the overall of this term would be a positive value. And when the different signs are added together, this is when the spontaneity depends on the temperature. The sign of delta G would depend on temperature. For example, at low temperature, when you have low value of T, the term positive here would be a low value. Therefore, in this case, the negative value will be able to override the positive value. Therefore, the overall delta G would be negative, indicate that at low temperature, the reaction would be spontaneous. On the other hand, at high temperature, when you have high temperature, the temperature multiplied by delta S, this term would be a big value of the positive. The big value of positive will override the negative. Therefore, the overall sign of delta G would be positive. It indicates that at high temperature, the reaction would be non-spontaneous in the forward direction because delta G is positive. And here is the summary of the 4 scenarios that I just mentioned. Let's take a look at example 10. Example 10 is an example of the warm pack reaction. In this case, we are going to determine the sign of entropy change of the system and also enthalpy change of the system. And we will take a look at how the temperature affects spontaneity as well. Again, the sign of entropy change of the system, we can look at how the change of the physical state going from reactant to the product. If you look at the equation, you will see that you have 3 mole of gas changing to 0 mole of gas, or you will see that you have solid and gas and it's become just a solid. Therefore, the degree of dispersal for the species in the reaction would decrease. Therefore, in this case, the entropy change for the system would be negative because the reaction becomes less dispersed. And for the enthalpy change of the reaction, we will look at whether the reaction is exothermic or endothermic. This reaction is the reaction of warm pack. Warm pack indicates that the heat is being released to the surrounding, or in this case, we know that the system emits heat. Therefore, this system would be exothermic. Therefore, the sign of the enthalpy would be negative. To determine the delta G sign, I'm going to use the delta G equation, which is delta G of the reaction would equal to delta H. And I'm going to separate this by the addition so that way it's easier for me to see how the temperature affected minus T delta S. Okay, and we know that because the delta H is negative, and we know that delta S is also negative. Therefore, if you're looking at the term between T delta S, this term right here, you are going to have a negative multiplied by negative. This term would be a positive value. Therefore, you are having negative add to a positive value. This is when the reaction is dependent on the temperature. If you think about this at high temperature, if you have high value of this T, then your value of the negative delta S would be a big value, right? Because you multiply a big a big temperature or high temperature to delta S. Therefore, the product of this term would be a big value of the positive. And the big value of the positive will override the negative delta H. Therefore, in this case, the result of delta G would be overall a positive value. In this case, we can say that it would be non-spontaneous in the forward direction. At high temperature. And if you do the same analysis at low temperature, and if you put in the sign of the delta H and delta S, you will see that at the low temperature, this term will become a small positive value because at low temperature, small t multiplied by delta S would give you a small value of positive. Therefore, in this case, the negative can override the positive, and the overall delta G will come out to be a negative value, indicate that this reaction at low temperature, it would be spontaneous in the forward direction. Looking at the sign of delta H and delta S sometimes is not easy. I'm going to teach you next how to actually understand these better by using the Le Chatelier principle to help us to understand this concept. I'm going to compare the difference between endothermic process and exothermic process. When we talk about endo versus exothermic process, we are looking at how the heat is exchanged between system and the surrounding. For the endothermic process, we know that the system is absorbing heat from the surrounding. Therefore, in this case, you will see that the delta H of the process or of the system would be a positive value because it's gaining heat from that. However, go back into chapter 17.2. In this case, you will see that the entropy change of the surrounding would be negative because the heat is become more concentrated in the system. Now let's take a look at exothermic. Exothermic would be the opposite process because the heat is being released from the system to the surrounding. Therefore, in this case, the delta H of the system would be negative because system losing heat, and the entropy change for the surrounding would be positive because the heat transfer into more dispersed environment, which is the surrounding. Next, the scenario that I'm going to take a look at is the change of the entropy for the system, which is how much the matter become dispersed. For the system, you are looking at how the physical state change. Let's say if the physical state change resulting in the decreasing of the entropy for the system, for example, going from liquid to solid, or going from gas to liquid or gas to solid, those are the result of decreasing of the entropy for the system. You will see that when you talk about the spontaneity here, you will see that if the entropy of the system or the dispersal of matter decrease, and also the heat dispersal also decrease as well, it's going to always result in non-spontaneous no matter what temperature it is. Therefore, in this case, if you have endothermic process with the decreasing of the dispersal of the matter, this would be an example of non-spontaneous process at all temperature. And you can either use the entropy change of the universe to help you to determine this as well, or you can use the delta G to help you determine spontaneity as well. It's going to give you exactly identical result because both dispersal of matter and the dispersal of energy, both of them decreased. Therefore, in this case, it will be non-spontaneous at all temperature. Next, for exothermic scenario, if you have the entropy change of the system or the dispersal of matter increased or become positive, for example, it's changing the physical state from solid to gas or aqueous to gas or solid to liquid, all of this resulting in the positive entropy for the system because the matter become more dispersed. In this case, if you're looking at the sign of entropy change for the system, the matter become more dispersed, and also the heat or the energy is also become more dispersed as well. Both matter and energy become more dispersed. Therefore, in this case, you are going to end up with the spontaneous process at all temperature. You can use the entropy change of the universe or the change of Gibbs free energy for the system to help us determine the relative size of the entropy of the universe and also the Gibbs free energy of the system as well. Whatever you do, you will see that for this scenario, the reaction would always be spontaneous at all temperature. In summary, when both dispersal of matter and energy decreased, you will see that the system would always be non-spontaneous at all temperature. Versus when you have the dispersal of matter and also energy increased, you will see that the spontaneous will always be, the reaction will always be spontaneous at all temperature. These two are an example of how the temperature has no effect on spontaneity of the process. Next, we will take a look at what if you have endothermic process where the dispersal of energy decreased, right, because it's more concentrated into the system. However, the dispersal of matter increased, what would happen? In this case, you know that when these two are the opposite, right? So when the dispersal of matter are the opposite of the dispersal of energy, then this is when the temperature is the spontaneity of the reaction would depend on temperature. When the spontaneity depend on temperature, you can either use these two equations to determine the relative size of delta S universe and delta G system, or you can use the Le Chatelier principle, which is a lot easier to predict spontaneity. According to the Le Chatelier principle, the reaction will be at equilibrium where reactant will convert into product. And for endothermic, it indicates that the reaction absorbing heat, which means that the reactant is the one that is absorbing heat. Therefore, the heat will be part of the reactant. And when the heat is changed, for example, at high or low temperature, it would cause the reaction at equilibrium to shift in order to establish the new equilibrium. Therefore, in this case, if the scenario that we have, let's say if this reaction is at high temperature indicates that we add heat to the system. Therefore, in this case, the system will try to minimize the disturbance by shifting toward the product to reduce the heat in order to reach the new equilibrium again. Therefore, in this case, the reaction would be spontaneous in the forward direction at high temperature. However, at low temperature means that you are lacking heat. Therefore, the system would shift toward the reactant in order to produce more heat in order to reach the new equilibrium again. Therefore, in this case, the reaction would be spontaneous in the reverse direction or non-spontaneous in the forward direction. Next, let's take a look at the exothermic scenario. Again, for exothermic scenario, this is when you have the increasing of the dispersal of energy. However, what if we have the dispersal of matter to decrease? In this case, you will see that the size of the dispersal of matter is the opposite of the size of the dispersal of energy in this case. Therefore, the spontaneity will depend on temperature also. Again, to determine the spontaneity of the process, you can either use these two equations to help us determine the relative size of the entropy change of the universe or the delta G for the system that we did previously. However, in this case, I'm going to use the Le Chatelier principle to help us understand easier. So I'm going to start with the reactant that are in equilibrium with the product. In the exothermic scenario, this is when the reaction is producing heat, which means that heat would be part of the product because the reactant converts to the product and releasing heat. In this case, if you have high temperature, when you have high temperature, you will increase amount of heat in the system. The system is not going to be at equilibrium anymore. It's going to have too much heat and it's going to shift toward the reactant to minimize that heat. Therefore, in this case, the reaction would be spontaneous in the reverse direction. Or non-spontaneous in the forward direction. Whereas if you have the reaction at low temperature means the system is lacking heat. Therefore, the system will shift toward the product in order to make more of the heat in order to reach the equilibrium again. Therefore, in this scenario, it would be spontaneous in the forward direction, or it would be non-spontaneous in the reverse direction. For myself, I find that it's easier for me to understand whenever that the spontaneity depends on temperature by using the Le Chatelier principle to predict spontaneity. It's easier than using these two to predict spontaneity. Let's take a look at example 11. Example 11 asks us to predict spontaneity of the reaction by giving us the sign of the enthalpy change and also of the entropy change of the system as well. According to sign of the enthalpy change of the system, this reaction is endothermic, which means that the dispersal of energy decrease in this case. However, if you look at the sign of entropy change of the system, we see that the dispersal of matter is actually increased, right? Because positive. So as you see, these two are the opposite. Therefore, this example would be the example that the spontaneity depend on temperature. Therefore, we can eliminate choice D and also choice A as well, because those two doesn't depend on temperature. Now between B and C, which one is the correct one? This is when I will need to use the Le Chatelier principle to help me understand better. For the Le Chatelier principle, for the endothermic process, we know that the reactant add to heat would become product. The reason why I add heat with the reactant is because this is an endothermic, right? The reaction absorbing heat. Therefore, in this case, to push the reaction forward, you will need temperature to be at high temperature, because at high temperature, you increasing heat, the reaction then will shift toward more of the product. Therefore, it's going to be spontaneous in the forward direction at high temperature. So the answer would be B. Let's pause the video and complete example 12 and then resume the video again when you finish. For example 12, we see that the delta H is negative. It tells us that this reaction is exothermic, which indicates that the dispersal of energy increased because dispersed throughout the surrounding, is not concentrated within the system. And if you look at the sign of entropy change of the system, this one tells us about the dispersal of matter. And we can see that the dispersal of matter is also increased as well. In this case, both dispersal of energy and matter, both of them increased. Therefore, this is an example of the spontaneity that doesn't depend on temperature. So the temperature has no effect on spontaneity. So what we can eliminate would be choice B and choice C. And because both of energy and matter become more dispersed, therefore in this case, this reaction would be spontaneous at all temperature, because the overall dispersal of both energy and matter always increase, it's become more spread out. So the reaction would be spontaneous at all temperatures. Example 13 is an example of the temperature at equilibrium, where the delta G is equal to 0, which indicates that reaction is already at equilibrium. In this case, in order to figure it out, the temperature at equilibrium, you will need to use the delta G equation, which is equal to delta H minus T delta S. And because it's at equilibrium, so we are going to set delta G equal to 0, and we are going to input the value of delta H, which is in this case would be negative 19.9. I'm going to change kilo into joule, so it would be multiplied by 1000 and change that to joule per mole. Okay, and we are going to add to the negative. We don't know what is the temperature, so I'm gonna leave it as unknown variable T. And the delta S is negative 55.5 joule per mole per Kelvin. Next, move this term to the other side of equation. You are going to get this term to be a positive value because you already moved to the other side. Thus, you are going to switch the sign for that. And divide both sides by negative 55.5 joule per mole per Kelvin. Then this term will cancel out, and also the joule per mole will cancel out. You are going to flip per Kelvin up, then the final unit of temperature will be in Kelvin, and you will get the temperature equal to 359 Kelvin. Make sure that the value of the temperature in Kelvin always have to be a positive value, because the lowest temperature for Kelvin is only 0, it can never be below 0. So if you get a negative value of the temperature, that indicates that you do the wrong or incorrect calculation. What does this temperature tell us? Well, this temperature tells us that when the reaction is carried out at 359 Kelvin, the reaction will reach at equilibrium, which means that both reverse and forward direction proceed spontaneously at equal rate. It also indicates that the spontaneous of this reaction is temperature dependent, and this temperature at equilibrium would be the tipping point, which means that outside of this temperature in Kelvin, the reaction can either be spontaneous or non-spontaneous. Because this reaction spontaneity depends on temperature and the reaction is exothermic. Therefore, to predict spontaneity for this, we can use the Le Chatelier principle to help us by write out the reactant that convert to the product. And because it's exothermic, so heat would be part of the product in this case. And we see that for the spontaneous process here, for the reaction to proceed forward, the amount of heat have to be low. Therefore, in this case, at low temperature, the reaction would proceed in the forward direction in order to produce more of heat, in order to establish the equilibrium again. Therefore, in this case, the reaction will become spontaneous at low temperature, which is going to be lower than 359 Kelvin. In conclusion, for this reaction, the reaction will be spontaneous in the forward direction at the temperature below 359 Kelvin, and the reaction will be non-spontaneous reaction in the forward direction at the temperature higher than 359. But for the temperature at 359 Kelvin, that's where the reaction is already at equilibrium. Let's pause the video and complete example 14. Resume the video again when you finish. For example 14, do the same thing as we did in example 13. You are going to use the delta G equation and replace delta G with 0 because the reaction asks the temperature at equilibrium. You will need to know that at equilibrium delta G equal to 0. Then plug in delta H in joule. Don't forget to convert kilojoule to joule. And then negative T delta S. And then you are going to move this term to the other side and divide by the negative 364.6 joule per Kelvin, which is the value of delta S. Then you are going to get delta T to be a positive value. Again, your delta T have to come out always to be a positive value, and the unit would be in Kelvin. Okay. Therefore, this is the reaction at equilibrium. This reaction at equilibrium or at this temperature is indicate that the reaction would go forward and reverse spontaneously, right? So the reaction proceeds spontaneous in the forward and reverse direction at equal rate at the equilibrium. However, at a temperature outside this range, then the reaction can either be spontaneous or non-spontaneous. And because this reaction has a negative delta H, is indicated this reaction is an exothermic reaction. For an exothermic reaction, the reaction would go forward toward the product, which is going to produce more heat at lower temperature. Therefore, the reaction is going to be spontaneous in the forward direction at temperature lower than 3483 Kelvin. Next, we will take a look at the thermodynamic functions at the standard condition versus non-standard conditions. Again, the difference between each of these terms, the only difference would be the north side that we represent on the top of each of those terms. The north side indicates at the standard conditions. Let's take a look at an example of evaporization of water at the standard state. At the standard state indicate that this reaction happened at 25 degrees Celsius, 1 atmospheric pressure and for the gas and 1 molar concentration for the aqueous solution. If you calculate the standard free energy change for this process right here by using the standard give free energy formation, you are going to obtain a positive value for this process. The positive value of the delta G naught tell us that at the standard state condition, water liquid will not evaporate into water vapor. But how come that at 25 degrees Celsius or 77 degrees Fahrenheit, we observe in our daily life that water still evaporates spontaneously? So how can we reconcile that? Note that when we consider the standard conditions, the pressure of water must be at 1 atm pressure at 25 degrees Celsius. Therefore, in this case, we will end up having the closed system of the water sample. In this case, yes, the reaction will not be spontaneous in the forward direction. Water will not vaporize. Instead, at this condition is indicate that the delta T is positive, is indicate that the water instead would condense to produce liquid water. Therefore, in this case, you will observe that water will not vaporize, but is going to condense spontaneously. However, in our real life example, we look at water sample with the open system, not the closed system here. Therefore, in this case, the partial pressure of water would be less than 1 atm because open to the atmospheric pressure in this case. Therefore, in this case, the pressure is less than 1 atm. So this condition is not at the standard condition. We call this at non-standard condition. And because this is non-standard condition, so the delta G naught would not apply for this case. Therefore, I cannot use this value to predict spontaneity at this process. So in conclusion, we can say that although the delta G naught at the standard condition is positive, but the reaction can still proceed spontaneously if the actual conditions are not at the standard state. Vice versa, if the standard free energy is negative, then the reaction can also proceed non-spontaneously as well if the actual conditions are not at the standard state. Here is the equation that expresses the relationship between the give free energy at the non-standard conditions versus give free energy at the standard condition. Note that the difference between these two is that the naught sign indicates at the standard condition. R is the gas constant. In this case, we are looking at the energy which is in joule. Therefore, the gas constant will be in the value that have the unit of joule per mole per Kelvin. Therefore, in this case, the temperature have to be in Kelvin, and Q is the reaction coefficient. It tells you about the ratio between the product over the reactant. It doesn't have to be at equilibrium. It can be at any point of the reaction. You can see that the relationship between the non-standard condition and the standard condition of the free energy is related by this reaction coefficient. Therefore, we are going to understand the relationship between these two by looking at the value of the reaction coefficient. Let's take a look at the first scenario when Q, or the reaction coefficient, is equal to 1. When Q is equal to 1, we know that the delta G at the non-standard would equal to the delta G at the standard condition. If you replace RT, Ln, Q, which is equal to 1, you will see that this term right here would eventually equal to 0 because natural log of 1 equal to 0. Therefore, in this case, we can say that when Q equal to 1, the delta G will equal to the delta G naught, which indicate that at this condition, the delta G that we are looking at would be at the standard condition no matter what. When Q is greater than 1, it indicates that this reaction is not at equilibrium yet. At this point of the reaction, there are more product concentration than the reactant. Therefore, the reaction would shift toward the reactant in order to reach the equilibrium. Therefore, in this case, delta G of the non-standard condition would be positive value, indicate that this reaction would be non-spontaneous in the forward direction. On the other hand, when Q is less than 1, it indicates that this reaction is not at equilibrium yet. At this point of the reaction, there are more concentration of the reactant than the product. So the reaction will shift toward making more of the product. So the delta G would be a negative value because it's going to be spontaneous in the forward direction. And when Q equal to the value of K, or when the reaction coefficient value is equal to the equilibrium value, these indicate that the reaction is already at equilibrium. And when the reaction at equilibrium, we can say that the delta G at the non-standard condition will equal to 0 joule per mole. Here is the diagram that represents the relationship between standard versus non-standard gift-free energy. The reaction that I'm going to use is going to be the same as what we see here is the vaporization reaction of water. At the non-standard state condition where the delta G is negative, it indicates that at this point of the reaction, we having more of the reactant than the product. Therefore, at this point, the reaction is not at equilibrium yet. It's going to proceed toward the product in order to produce more of the product. Therefore, it's going to be spontaneous in the forward direction until it reaches equilibrium where the potential energy would be the lowest. However, at the standard condition of the water vaporization where the delta G is a positive value, the positive delta G tells us that at this point, at the standard condition here, we having more of the product. Therefore, the reaction would shift toward the reactant in order to reach the equilibrium again. So it's going to be spontaneous in the reverse direction until it reaches equilibrium again. Note that the lowest chemical potential is where the free energy is equal to 0. The negative or positive side is just tell you about the direction of how it's going to proceed. Whether it's going to proceed spontaneously in the forward direction or it's going to proceed spontaneously in the reverse direction. But the absolute value, which is 0, would be the lowest chemical potential. Next, we are going to take a look at the relationship between the gift-free energy at the standard condition and the equilibrium constant. We see from the previous page that the gift-free energy change of the reaction at the non-standard condition is equal to the change of the gift-free energy of the reaction at the standard condition plus gas constant times temperature multiplied by natural log of the reaction coefficient. For the reaction at equilibrium, we say that the Q is going to be equal to K. Therefore, I can replace these with the K. KEQ refer to any type of equilibrium constant. It can be KC, it can be KP, it can be KA, KB, KW, KSP, which is of these express the equilibrium constant for a specific reaction. KC from what we KC and KP from what we learned in Chem 122 is represent the equilibrium constant by the concentration, and this is by the pressure. Ka and Kb are the equilibrium constant for the acid and base. Kw would be the equilibrium constant for water ionization, and Ksp would be the equilibrium constant for the solubility product. So if I do that, replace Q by K because it's at equilibrium, then I also can replace the delta G to be 0 as well, because we know that at equilibrium the delta G would equal to 0. Then if you change this, if you move this term right here to the other side, if you move this term to the other side of the equation, you are going to get delta G naught, or the gift-free energy change at the standard condition, equal to negative RT ln K. Okay, so again, this K can be any K. And again, the reason why it's negative because we are changing this term right here to be on the other side. So you will need to also change the sign as well. If you rearrange this equation, we can also get the fact that you can calculate the equilibrium constant value by using the gift-free energy change as well. This equation right here is used when the problem asks you to find out the Gibbs free energy and is giving you the equilibrium constant. This equation here, you can use this equation when it asks you to find out the equilibrium constant and the problem gives you the free energy value. We know that the equilibrium constant is coming from the ratio between the product over the reactant. Therefore, when you have the equilibrium constant value that is greater than 1, is indicate that you at that point, at that equilibrium point, you have more of the product than the reactant. So in this case, we have product more abundant. In this case, the delta G would be a negative value because the reaction would proceed toward the product, right, to form more of the product. So it would be spontaneous in the forward direction because the reaction is produced more of the product. However, when the equilibrium constant is less than 1, it indicates that at the equilibrium point, you have more of the reactant than the product. So at equilibrium, the reactant would be more abundant. In this case, it tells us that the reaction did not proceed far at all. Is mostly stay as the reactant. Therefore, the delta G would be a positive value, indicate that the reaction is non-spontaneous in the forward direction. That's why it doesn't produce a lot of the product. Majority of them still stay as the reactant. And when the equilibrium constant value K equal to 1, we can say that if this is equal to 1, the natural log of 1 equal to 0. Therefore, in this case, the delta G naught will equal to 0. It indicates that the composition at equilibrium mixture between reactant and product are comparably abundant. Let's take a look at example 15. Example 15 gives us the chemical equation with the Kp value, and this is the equilibrium constant with respect to the pressure at 25 degrees Celsius. It asks us to calculate delta G at 25 degrees Celsius under the following conditions here. The first condition that it gives us is at the standard condition. It asks us to find out the delta G at standard condition. Therefore, in this case, it's pretty much ask us to find out delta G naught, because delta G naught is indicate the Gibbs free energy at the standard condition. The Gibbs free energy at the standard condition can be calculated from the equilibrium constant. So in this case, it would be negative RT ln K. And again, as I mentioned earlier, the KEQ is referred to any type of equilibrium constant. It can be KC, KP, KA, KW, KB, or KSP. It can be any of those K. So to find the delta G, the standard Gibbs free energy for the reaction, we will need to replace the value of gas constant R, which is 8.314 joule per mole per Kelvin. Therefore, the temperature would be in Kelvin. So change 25 degrees Celsius into Kelvin, you will get 298 Kelvin. And then take natural log of K, which is the equilibrium constant, is given equal to 81.9. Do this math, you are going to get Gibbs free energy equal to negative 1.09 times 10 to the 4th. And for the unit, you will see that the unit of Kelvin will cancel out. Therefore, in this case, the unit of Gibbs free energy will be in joule per mole. The negative delta G for the standard condition tell us that at the standard condition, this reaction would proceed spontaneously in the forward direction. For B asking for the value of the delta G at equilibrium. And we know that at equilibrium, the delta G of the reaction will always equal to 0 joule per mole. So you don't need to calculate anything. The answer would be just 0 joule per mole. So that would be the answer of delta G at equilibrium. You will need to know this value. Okay, so now next C give us the pressure of each of those species, and you can see that the pressure that we are given is not at 1 atm. It indicates that this condition is not at the standard condition. So this condition at non-standard condition because the pressure is not at 1 atm. So this is non-standard condition. Therefore, in order to find out the delta G for this non-standard condition, is going to equal to the delta G naught, which is at the standard condition, plus RT ln Q. Okay, so which means that if you want to find out the delta G at the non-standard condition, you need to know delta G naught, which we already calculate that. You also need to know Q, which is the reaction coefficient. Reaction coefficient is similar to K, which is the ratio between the product over the reactant. Therefore, in this case, you can plug in all of these values. So the delta G naught, I'm going to plug that in, which is negative 1.09 times 10 to the fourth joule per mole. Okay, then I'm going to add gas constant, which is 8.314 joule per mole per Kelvin. Okay, then then multiply by the temperature in Kelvin, which is 298 Kelvin. Okay, and then multiply by ln/Q. Okay, so Q again is the ratio between the product concentration. So in this case, it's giving us pressure. So you can just use partial pressure that is given, which is going to be partial pressure of ICL. So it's going to be 2.56. And because the product has 2 as a coefficient, you will need to square this value, divide by the partial pressure of the reactant, I2, which is 0.333. Multiply that by another reactant, which is the chlorine, 0.221. And do the math. You are going to get delta G equal to 222 joule per mole. The reason why the unit is joule per mole again, because the Kelvin cancel out, so you're going to end up with joule per mole. The positive delta G at the non-standard condition tell us that at this condition, the reaction is non-spontaneous in the forward direction. Example 16 asks to calculate the equilibrium constant for the reaction. Is giving us delta H and delta S. Whenever the enthalpy change of the reaction and the entropy change of the reaction is given, you will need to be able to relate these to the delta G. Right? Therefore, in this case, we can find out the equilibrium constant K by using this equation right here because involved with the delta G. Because the enthalpy change of the reaction and entropy change of the reaction have the naught sign, it indicates that the delta G that we are going to calculate would be the standard change of the given free energy with the naught sign as well. Plug in all of these values. Don't forget to change the kilojoule into joule from the enthalpy of reaction, and then convert temperature into Kelvin as well. You are going to get the given free energy equal to negative 22,000 joule per mole. In this case, it tells us that the negative delta G is tell us that this reaction is going to be spontaneous at this condition in the forward direction. And when you plug in the delta G into the equilibrium equation, the equilibrium constant equation, you are going to do a negative of the value of the delta G divided by the gas constant times the temperature, and e to that power, you are going to get the equilibrium constant to be around 8,000. Again, equilibrium constant has no unit. Therefore, if you check the unit, all of this unit will eventually cancel out. Therefore, the equilibrium constant will have no unit. This reaction, since the reaction is has a negative delta G, is indicate that this reaction is spontaneous in the forward direction, which means that at equilibrium, you are going to end up having more of the product than the reactant. Therefore, the K value that you observe here would be a high K value, indicate that at the equilibrium, you have more of the product than the reactant. It indicate that reaction is proceed far to the right toward the product because it is spontaneous in the forward direction. Please practice more of this concept by doing the DIY problem. The answer key for this DIY will be posted on Moodle. please do not hesitate to contact me if you have any question about this topic. And also please join me during the live session on Thursday at 11 a.m. as well. The link to the live session on Thursday is posted on Moodle.